In this video, we are going to look at redox chemistry for a general chemistry audience. Okay, so redox is the title, but it's actually short for two separate words. So the read from redox comes from the word reduction. And reduction means to well, one way to think of it is gain electrons. And then ox comes from oxidation. And oxidation, a way to think of it is to lose electrons. Okay, the nice thing about capping it into the single word redox is it reminds us that you can't have oxidation without reduction. So the word redox reminds us that oxidation and reduction occur together or not at all. And we can see why that happens. We can see why they have to happen at the same time. Let's say, for example, you have an element that loses electrons. So let's say we have X plus and an electron. So originally element X, over time with the arrow, it becomes a positively charged ion. So it becomes a cation. Cation is a positively charged ion. And it's lost an electron. So we know that this is oxidation. Right. Whenever you have an electron as a product, we know that that's because you've produced it, so the thing on the left of the arrow has lost it. So that must be oxidation. Well, where did the electron go? So it had to go somewhere, right? So let's say you have Y, that electron had to go somewhere. So let's say it went into Y to form Y minus, which is an anion. Whenever we have electrons as reactants, it's because we've gained. So this is reduction. We have an electron as a reactant. Okay, so these two processes, this whole thing is redox. So if we were to take these two equations and recombine them again, if we took these two equations, combine both equations, then we'd essentially have everything on the left. See if I can do it here. We'd essentially add everything on the left of the arrow and combine it together. And then we'd have everything on the right of the arrow and combine that together. So that would be X plus an electron plus Y, right? That's all the reactants, to give X plus an electron plus Y minus. Okay? Now, we would have to do something called, which you would do in any math class, we cancel spectators. And a spectator is just common to both the reactant and product. Okay, so like terms in math, you would just say like terms. So anything that's common to both sides we can cancel. And you can see here that an electron goes in and an electron comes out. So the electron is a spectator. X goes in and Y goes in, but then X plus comes out and Y minus comes out. So the net effect, or the net equation, so overall, we have X plus Y to give X plus and Y minus. So that would be the net expression. Okay, so you can see that our electron exchange process had to happen at the same time. The electron that was lost had to go somewhere, it had to go into the other element. So again, you cannot have reduction without oxidation. There are ways that some people like to remember this. So there are some acronyms. You can remember the acronym oil rig. So oxidation is loss, oil of electrons. Reduction is gain, Ig of electrons. So that's one acronym that people like to use. It's not the only one, and you can certainly make up your own. Another acronym that some people like to use is Leo grr. So Leo the lion goes grr. So this is loss of electrons is oxidation. As Leo, loss of electrons is oxidation. Gain of electrons is reduction. Grr. Some people like that. It doesn't matter as long as you know how to interpret questions and you have an understanding of content. Okay, so some people like that one. So pick one. They both say the same thing, whether oil rig, Leo grr, but that would be something you would be expected to know. Obviously, if you have electrons as products, you have oxidation. If you have electrons as reactants, then you have reduction. And these are all saying the same thing. So whichever makes most sense to you. And the other way, which we need to get to now, is oxidation numbers. So let's have a look at that. Oxidation states. Oxidation state, oxidation number are essentially the same thing. The number is 0 for all elements, regardless of state. So when I mean state, I mean solid, liquid, gas. So it doesn't matter. If you have an element, it has the numerical value of 0. One way that I like to tell my students, and again it's an analogy, it's not to be taken too seriously, but the oxidation state of a chemical species, it would be analogous to the mood of the element. So just like you and I can have different moods, same person, different moods, we're influenced by our environment, then elements can have different moods, so to speak, influenced by their environment. Okay, so let's look at some examples of oxidation numbers. Okay. So let's see. Let's take a balanced equation. So we have 4 iron atoms and 3 oxygen molecules. And this gives 2 molecules of Fe2O3. Okay, so this is a balanced equation. And we're going to use what we said earlier on, that all elements are 0 oxidation state. Typically with oxidation states, you write them above or below the element as regular numbers in parentheses. And every element in, whether it be an element itself or an atom in a compound, has to have its own oxidation state. So I'm going to do them in red, and I'm going to do them below. So iron is an element. I've got 4 of them. The coefficient 4 doesn't matter here. So I have a 0 oxidation state atom. Oxygen here is a molecule, but it's elemental because it's only one type of element. So we treat this like an element, and again, it has 0 oxidation state. Here we have iron 3 oxide. So we know that this, from our nomenclature, this is iron 3 oxide. Try and write it without writing all on top of it. So iron 3 oxide. So we know from our nomenclature that the stock notation gives you the charge. Let's see, maybe I've got room to put an extra rule above. Yeah, I do. I'm going to go ahead and insert another little rule here. The oxidation state is same as the charge for monatomic ions. So a monatomic ion is just an ion made up of one atom, which is what we have here. So let's scroll down and look at iron 3 oxide. So iron 3 oxide, just some scratch work down here. Iron 3 oxide, we would essentially have to do a little tiny algebraic equation here. So we know that we have 2 iron 3s and we have 3 O2 negatives, right? That's what this would break up into if it's separated into free ions. And we know that the cation here, the 2 multiplies the 3 and we have a +6 charge here. The 3 multiplies the 2 and we have a -6 here. And the +6 and the -6 comes together to give a 0 net charge. So it's an ionic compound. There's no residual charge on it. Okay. We also can see that we have monatomic ions. So these are monatomic. So if I look at ion 3+, that tells me that the oxidation state on ion is +3. Typically with the charge, you write the number before the sign. With the oxidation state, it's more common to write the sign before the number. Oxygen, O2 negative, is the anion. Here, it's a monatomic ion with a -2 charge, so that would be the -2 oxidation state. So again, looking at this equation again, we have ion as an atom on the left, element, so it has 0 oxidation state. 2 oxygen atoms, but it's elemental. There's one type of element, 0 oxidation state. Here we have an ionic compound made up of monatomic ions. We separate the ions, we look at the individual charge. So iron here in iron 3 oxide has a +3 oxidation state. Oxygen has a -2 oxidation state. Okay, I'm going to erase this scratch work down here so we can do some more examples. How about hydrogen plus chlorine to give 2HCl. Again, hydrogen is elemental. There's one type of atom, so oxidation state 0. Chlorine is elemental, one type of atom, oxidation state 0. HCl, depending on depending on the phase. So I don't want to appeal to any purists out there that are going to say, well, if it's a gas, it's technically, we don't really care. That's minutia at the best of times. So let's just look at the fact that this would become H plus Cl minus. Okay. H plus Cl minus, so H plus would be a +1 oxidation state. Cl minus would be a -1 oxidation state. Done. No conversation about aqueous acidity, irrelevant. And we just don't want to get bogged down with the legality of it. Too busy learning chemistry. Okay, how about something like this? So I just want to do a few examples on this page, a little bit of repetition. 2 lots of silver and H2S to give Ag2S and H2. Again, silver, we have an element, all elements, oxidation state 0. Doesn't matter if it's solid, liquid, gas. H2S, this is not an ionic compound, it's a covalent compound, but we can kind of treat it as an ionic compound. We know that it's got a net 0 charge, and we're familiar that H can form H plus. So why don't we do this? Why don't we acknowledge the fact that the whole thing has no charge? If I had to guess who is the more dominant element, I would say it's sulfur. Sulfur, we know, likes to form a -2 charge. It's in the same family as oxygen. And I know that hydrogen, and I've got 2 of them, likes to form a +1 charge. So my contributions, the 2-to-1 ratio of hydrogen to sulfur, I've got 2 +1 hydrogens and 1 -2 oxygen, and they indeed sum to 0. So here's my monatomic charges. So I can say that hydrogen is in the +1 oxidation state, and sulfur is in the -2 oxidation state. So we kind of treat it like it's ionic. Silver sulfide, again, you may or may not know that silver likes to form a +1 charge. In fact, let's say you didn't. We have a metal and a nonmetal, so silver is the metal, sulfur is the nonmetal. This is an ionic compound, so we know that it sums to 0. And I would preferentially say that the non-metal, on this occasion sulfur, forms a -2 charge. And let's say I didn't know what silver did. I would just call silver X and acknowledge I have two of them. So 2, whatever silver's going to do, plus the single -2 charge on sulfur, sum to 0. So I have 2x minus 2 is 0. And if I keep going with the math, I know that 2x is plus 2 or x is plus 1. So I could arrive at my two oxidation states by doing a little algebra calculation here. So silver is plus 1. Again, we don't worry the fact that there's two of them. There are 2 plus 1 silvers. There's not 1 plus 2 silver. There's 2 plus 1 silvers. And again, sulfur is -2. And hydrogen is elemental, so oxidation state 0. Okay. Maybe a couple more examples. What about, yeah, actually we'll do one more example and then we'll shift to something else. What about 2 lots of cobalt and 3 lots of water to give this scary looking thing, cobalt 3 oxide. So not too scary, I guess. And that. Okay, let's do the easy bits first. Cobalt's an element, oxidation state 0. Hydrogen, one type of atom in a molecule, so it's elemental, oxidation state 0. Let's look at this covalent compound. I know that oxygen and hydrogen form water, and I know that the sum of the charges are 0, or water is a neutral material. And I know that oxygen is much more dominant in terms of electronegativity, for example, or strength, broadly speaking, than hydrogen. And oxygen likes to form a -2 charge. Hydrogen likes to form a +1 charge. So I've got 2 hydrogen and 1 oxygen. So here are my oxidation states. +1 for hydrogen, -2 for oxygen. Okay, cobalt 3 oxide. Let's say it's not that I don't know it's cobalt 3, but let's acknowledge that cobalt can form more than one type of oxidation state. Oxygen typically can't, so let's acknowledge that the whole compound has no charge because it's ionic, no residual charge. But I have 3 -2 charged oxygens, and I have 2 whatever cobalt's going to be today. Okay, so I just have to solve for the oxidation state of cobalt. So I have 2x minus 6 is 0. Take the 6 to the other side. 2x is plus 6. If I divide both sides by 2 now, I have x is plus 3. So that's why we were saying cobalt 3 oxide. So plus 3 for cobalt, -2 for oxygen. Okay, so that's good. What if, let's actually do a couple more, because I haven't shown you any examples where we're initially offered out the gate a charge. So let's take a second to look at that. What if we had something like MnO4 minus, or permanganate as it's commonly known, S2O3 2 minus to give S4O6 2 minus, and manganese 2 plus. Okay, so this here obviously has been stripped of spectator ions. but we would approach it in exactly the same way. Here, this whole structure has a -1 charge. So that -1 here, that's our -1 charge overall. I know that oxygen is a nonmetal and it is highly more electronegative compared to manganese. So I'll give it preferential treatment. I have 4 -2 oxygens. And then manganese as a transition metal can have a variety of oxidation states. So I'm going to solve for it on this occasion. And I just have one of them. So look at the equation. 1 manganese, which I'll call X, plus 4 -2 oxygens equals a -1 charge. So X minus 8 is -1. I can add 8 to both sides, so X is +7. So manganese here is in the +7 oxidation state, and oxygen is in the -2 oxidation state. Okay, this structure here, the whole thing is -2. Again, I get the -2 from this residual charge here. I've got 3 -2 oxygens, and I've got whatever sulfur is on this occasion, which I'll call X, and I just have to solve for what sulfur is. So I've got 2x minus 6 is -2. I can add 6 to both sides, so 2x is +4, or x, if I divide by 2, x is +2. So +2 for sulfur, -2 for oxygen. Here, again, I have the whole thing as -2 because the residual charge. I have 6 oxygen on this occasion, so 6 -2 oxygens, and then 4 whatever sulfur is. And I have to solve again. So I've got 4x minus 12 is -2. Add 12 to both sides. 4x is 10. Okay. Scroll that down. If I divide by both sides now, so obviously I've picked a very unusual example. Let me just double check my math. Okay, so 4x -2 is -2. 2 6s are 12. Yes, that's -2. Let me check here. So if I add 12, I'm basically subtracting 2. Okay, just making sure my math was good. So x, now this would be reasonable for a general chemistry class, maybe a bit too tricky for an introductory class. But we're here, so let's have a look at it. You can't have a fraction of an oxidation state, but you can have a mixture of oxidation states that when averaged give you a fraction. Okay, so obviously if I divide 10 by 4, I'm going to get a fraction. So I'm going to get essentially a mixture of +2, and let's see, I'm going to grab my calculator real quick. So 10 divided by 4. Yeah, so let me be careful here. So out the gate, it looks like you would have plus 2.5, which is wrong. Okay, so you can't write a fraction of an oxidation state. So what you would do, you would acknowledge it's the sulfur, right? So I've got 4 sulfur. So you'd have S, 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 S. We've got to average these so that it equals 2.5. So we could have plus 2, plus 2, plus 2, and plus 3. Let's see what that averages to. 6, 9, 9 divided by 4. That would be 2.25. All right, we need another 3. So let's try that. 6, 10, 10 divided by... Yeah, so that's what we have. So we essentially take the average of all of these. It equals 2.5. So that's how you would think of this unusual example. So again, we can't say that x is a fraction. That would be the wrong... it's just a mixture of oxidation states. That would be correct. Okay, so that was an unintended little surprise. Okay, so we've seen that. Let's move on before this video gets too long. Okay, next thing I want to move on to now is oxidizing and reducing agents. Oxidizing and reducing agents. Oxidizing agents undergo reduction. Reducing agents undergo oxidation. Okay, so let's see an example. Let's have a look at, oh, one other thing, very important. Agents are always reactants, never products. And the agents are always the entire reactant, never single elements within a reactant. Okay, so let's see an example of 3. Okay, so let's have a look at chlorate and chloride to give Cl2, chlorine, and chlorine dioxide. Okay, so first thing I would suggest that you do is write oxidation states. So we know that this whole thing is -1 because of that charge. I've got 3 -2 oxygens, and I've got whatever chlorine is on this occasion. So I've got X minus 6 is -1. Add the 6 to the other side. X is +5. Okay, so I've got chlorine plus 5. I'm going to put it above here. Above or below doesn't matter. And then oxygen is -2. Okay. Monatomic ion is just the charge, so -1. Element, 0. 0 charge, there's no charge. I've got 2 -2 oxygens, and whatever chlorine is in this occasion. So I've got x minus 4 is 0. Add 4 to both sides. X is plus 4. So plus 4 for Cl, -2 for oxygen. Okay, so I'm going to get rid of my scratch work on the video. Just erase that scratch work, because the scratch work was to get us the oxidation states, right? Now let's go on to look at the agents. This is the new skill here. Okay. Do it in red. Okay, so I'm going to write what I call, well, not just what I call, people call half equations. So half equations. Half equations got nothing to do with half or 50%. It just means look at every chemical individually as a reactant and a product. So let's see what's changing. You can really gauge which is the appropriate half equations by looking at what changes. So clearly oxygen is not changing here. Oxygen is in the -2 oxidation state on the reactant side. It's in the +2 oxidation state on the product side. But we can clearly see that this chemical is connected with this chemical, and this chemical is connected with this chemical. So I would write ClO3 minus is connected with ClO2. That would be a half equation, and I've got Cl minus is connected with Cl2. Okay, now if you're going to look at balancing redox equations, which I'm not in this video, we would have to worry about the things that are not changing as well. So I'm going to say if you're going to balance redox, we would have to worry about all elements. But in this video, we are not going to worry about balance in redox. We are just going to worry about things that are changing in oxidation state. So if you are not going to balance redox, we are just going to ignore elements whose oxidation state doesn't change. So we're only interested in, let's see, we are only interested in, well, let's see if I can copy and paste this. I only want the black text, but I'm probably going to bring some friends along for the ride. Let's see if I can copy and paste this on the next page. Yep, kind of. So I'm going to get rid of the bits we don't want, and we'll focus on the bits we do want. Okay, not too bad. So we'll put our oxidation states back in. Can't remember what they were now. We had +5, -2. Alright, so we had +5, -2, -1, 0, +4, -2. Alright, that's what we had. We're only interested in the things that are changing, because again, we're not interested in balancing equations in this video. That would be for another video. So let's look at the chlorine. So let's draw our half equations. We have Cl in the +5 oxidation state, given Cl in the +4 oxidation state. All right, that's, for example, from A, and then from B we have Cl in the -1 oxidation state, giving Cl2 in the 0 oxidation state. Okay. Again, I'm not worried about balancing, so don't worry the fact that there's 2 Cl's here and there's only 1 Cl there. We're just looking at oxidation states in this video. Okay. And in fact, to echo the fact that we're really not interested in making this balance, let's get rid of that too. So we're just looking at the elements. Okay, so if I've gone from a +5 oxidation state to a +4, I must have lost plus charge, so I must have added an electron over here. Because 5 positives and a negative gives 4 positives. So I've got a gain of electrons, so I know that A is reduction. If I've gone from a +1 oxidation, a -1 oxidation state to a 0, I must have lost an electron as a product. So I know that I've got an electron as a product. This is oxidation. So the whole process is redox. But more importantly, now I know exactly which the agents are. So remember, let's use a different color. Let's use blue. Okay. So I know that the agents are here somewhere. These are my agents. So I'm not going to look on the product side. So let's look at half equation A. That involved the agent, whatever the agent was on the left, the ClO3-, chlorate. I know that chlorate underwent reduction. So I know that chlorate underwent reduction, right? And I know that chloride in half equation B underwent oxidation, right? And I know from my definition that the oxidizing agent undergoes reduction. So I know that ClO3- is the oxidizing agent. And I know that the reducing agent undergoes oxidation. So Cl- is the reducing agent. Based on the information I've been given. Okay, notice I don't just say Cl. The Cl is helped along by the oxygen and chloride, so I have to acknowledge the whole specimen when I label the agents. Okay, Let's see, maybe we can do one more example before this video gets too long. And then for my students, I have a worksheet with about 35 examples and answers that you can practice. Okay, let's have a look at, I don't know, I'm trying to find a quick example here. Try and find one without charges in, might be a good idea. Yeah, let's have a look at, I think this is one we've already looked at, but let's look anyway. So I've got that's another example. 4 iron, I think this is the first example we looked at. This is just an example without charges. To give 2 iron 3 oxide. Okay. Again, let's put the oxidation states in. Zero for the elements, and then we have +3 and -2. Recall that we had 2 lots of +3 iron and 3 lots of -2 oxygen to give a neutral charge. Okay, so that's where the +3 and the -2 came from at the start of the video. Let's write half equations. So clearly the iron is going into the product, but also the oxygen is going into the product too. So it doesn't matter if you don't have the same number of reactants and products. So let's write half equations. Again, I'm not really interested in balancing, although this equation is balanced a priori, so we could acknowledge the fact that it's balanced, that's okay too. So 4 iron are clearly given 4 iron again. But I've got an oxidation state change from 0 to +3. And so let's call that A. Let's call this one B. So that's A. And then B, we've got 6 oxygen in the 0 oxidation state to give 6 oxygen in the -2 oxidation state. Again, not really bothered about balancing in this video. This equation just happened to be balanced anyway. Okay, well, you've got 0 charge becoming 3 plus. Well, it can't. The charge has to be the same. So the 4 hits the 3, so I've got 12. So to get rid of 12 plus charges, I have 12 electrons. So 0 charge or 0 oxidation state on the left, 0 oxidation state on the right overall when you sum all the charges. I've got electrons as a product. This must be oxidation. Notice now we can see that the oxidation state increases. If the oxidation state increases, that's also a symbol of oxidation. So an increase from 0 to +3 is a testament to oxidation. An oxidation state decrease from 0 to a negative number is a hallmark of reduction. Well, where did the -12 come from? It came from these -12 electrons over here. Notice in half equations, you always have electrons on opposite sides. So if you have electrons as a product in one half equation, another half equation must have the same number of electrons as a reactant. Okay, so here's our redox again. They occur jointly or they don't occur at all. The oxidizing agent undergoes reduction, so I know that, let's change this to blue again. I know that this entire structure is the oxidizing agent. Because it was half equation B, and the oxidizing agent undergoes reduction. And I know that the reducing agent undergoes oxidation. So this chemical, not really the number 4, but just the chemical ion. So maybe I can be a bit more careful with which I bubble in. All right, it's not going to let me get rid of that. The element, I didn't really intend for the whole coefficient to be bubbled too. So just oxygen, it's irrelevant to the fact you have 3 of them. Just oxygen is the oxidizing agent, and just iron is the reducing agent. Okay, so again, for my students, I have a wealth of practice problems to try. This video should set them up to be getting on with that classwork. So this summarizes what I would like my students to know about reduction and oxidation chemistry at this introductory level. You could build upon this to look at balancing equations in redox, look at the effect of redox on pH, some biomedical applications of redox, some electrochemical applications of redox. In this video, we won't be doing any of that though, but look out for subsequent videos where we might do that. Okay, and that concludes this video.